Mechanical testing. How materials respond to forces. It's essential data for design. Defining the limiting data that a structure can withstand without failure. Mechanical tests are broadly divided into two types: quantitative and qualitative. Quantitative tests give numerical results that are used for design, whereas qualitative tests are used for making comparisons. Well, in this short introduction to mechanical testing, we'll be looking at tensile testing, bend testing, Sharpie and CTOD testing, hardness testing, and lastly, the weld break test. So, off we go. Tensile testing, both a qualitative and quantitative test. In a nutshell, a suitably prepared specimen like this, machined to dimensions dictated by the codes, is pulled apart uniaxially at a specified rate. Both the load and the test piece extension are continuously measured and recorded. So, from this test, we can create a stress-strain curve defining the ultimate tensile strength and the yield point. In other words, measures of the material's strength, as well as the percentage elongation and the percentage reduction in area, both measures of the material's ductility. And the slope of the elastic portion of the curve, essentially a straight line, gives us the Young's modulus. Unlike the tensile test, the bend test provides a purely qualitative result that can be used to evaluate both the ductility and the soundness of the material, usually a weld section. It's often used for quality control of butt-welded joints. Both the test piece and the test equipment are simple. The test uses a coupon that is bent in three-point bending to a specified angle. Since the outside of the bend is extensively plastically deformed, any defects or signs of embrittlement are quickly revealed. The test kit itself varies from the popular male-female former to the wraparound bender, rather like a plumber's pipe former. The strain applied to the specimen depends on the diameter of the former, which is specified in the test standard and is related to the coupon thickness. The angle may be 90, 120, or 180 degrees, and may be face, side, or root bends. Now, measuring the toughness of a material demands different equipment altogether. Toughness is broadly a measure of the amount of energy required to cause an item to fracture and fail. To measure this, we most commonly use the Sharpie V-notch test. It involves striking a standard notched specimen with a controlled weight pendulum, travelling at a set speed. Only a little material is required for each specimen. They're 55 mm long, 10 mm square, and have a 2 mm deep notch, but can be smaller for thin materials. The specimen is struck on the opposite face to the notch. It's fractured, and the pendulum swings through by a specific amount, giving a measure of the energy required to break the material. The amount of energy absorbed in fracturing the piece gives an indication of the notch toughness of the test material. If a small amount of energy is absorbed, the material is brittle. Ductile materials absorb a great deal of energy. Experience indicates that a specified energy absorbed is required to avoid brittle fracture. Measuring fracture toughness accurately, in a way that can be related to a tolerable flaw size, is a job for the crack tip opening displacement test, or CTOD as we call it. Unlike the small, inexpensive Sharpie specimen, the CTOD specimen maybe the full thickness of the material. It contains a genuine fatigue crack and will be loaded at a rate representative of the service conditions. As the name suggests, the crack tip opening is measured throughout the test and may be used in fitness for purpose assessments. As bending proceeds, the crack tip plastically deforms until a critical point is reached, when the crack has opened sufficiently to initiate a fracture event, and either partial or complete failure of the specimen. Many specimen geometries may be used, and this type of test piece is known as the single-edged notched bend, or SENB specimen. The compact tension, or CT specimen, may also be used to characterize fracture behavior. It's similar to the SENB specimen in that it's a proportional specimen of full plate thickness, containing a deliberately introduced fatigue crack. CT specimens require much less material to manufacture, but are considerably more expensive to machine. CTOD tests enable critical floor sizes to be calculated and decisions made about fitness for service, or the required level and sensitivity of non-destructive examination. So they are quantitative tests. There are, however, a number of qualitative tests which dictate a go or no-go result. Typical of these is the nil ductility temperature test. It's confusingly dubbed the NDT test. The sample size is standardized, depending upon plate thickness. A brittle crack is introduced on one side, and the simply supported specimen is struck in a standard way. The test is carried out on a number of specimens at progressively lower temperatures until the test piece breaks in a brittle fashion. This is known as the nil ductility temperature, or NDT. Now, hardness testing is something different altogether. The term hardness has several meanings, but it broadly means resistance to indentation and is a measure of tensile strength. The Vickers hardness test uses a pyramid-shaped diamond indenter, which of course doesn't deform at high loads. By lowering the indenter under a standard load for 30 seconds onto the surface of the sample, it's possible to calculate the hardness by measuring the impression it leaves. Needless to say, the indenter dimensions and the loads applied are standardized in the codes. The Rockwell hardness test, named after the American Stanley Pickett Rockwell, works on a similar principle, with a conical indenter, but uses 2 applied loads. The permanent increase in penetration depth is used to calculate the Rockwell hardness number. Different loads are used for materials with different hardnesses. The most common scales are Rockwell B and Rockwell C hardness. Now to specialist hardness testing, for determining hardness in cramped environments, or in-service components too large for the test laboratory, or indeed on very small samples. There are 3 common methods: the Knoop test, the Vickers test, and the micro-hardness test. Both the Knoop test and the Vickers test use a pyramid-shaped indenter. The loads are scaled down appropriately to between a gram and a kilogram, and produce impressions that require 100 times magnification microscope to see and measure. Finally, the fillet fracture or weld break test, a simple and very crude test to examine a weld's soundness, often in a production environment on the shop floor. 2 plates are welded together on one side only in a T configuration. Of course, the base metal, weld metal, and welding parameters must adhere strictly to those prescribed in the welding procedure under scrutiny. The fillet weld is notched with a saw cut along its centre line. Force is then applied to the specimen to bend open the weld using a testing machine, a press, or blows from a hammer. The fractured surfaces can then be examined for internal defects such as porosity, incomplete root penetration or sidewall fusion, and slag inclusions. Well, that about wraps up this brief introduction to mechanical testing. To learn more about any of the tests we've covered, why not contact TWI on 44 if you're outside the UK, 1-223 899 000. Or why not visit the website, that's www.twi.co.uk.